Okay, let's continue to the next video sections of this point cloud video series. In these sections, we will start to discuss the first paper, this PointNet from CVPR 2017. And this is, I consider this as the pioneer of the 3D understanding in the point cloud data. We call it PointNet. Okay, let's start. We will discuss first about the motivations why this paper, this research works exists. As we know from the previous video sections that point cloud is a sparse representations of the 3D model, right? So it means that if we use these sparse representations to carry a 3D understanding or 3D recognitions, we will have the computationally efficient, computationally cheap. However, there are some challenges that are related to the data properties of the point cloud itself. The first is irregular data format. We know that, for example, if we have an image, a pixel, for example, like 100 by 100, we will have the coordinate of the pixel, right? Like this is the 1, 1, 1, 2, 1, 3, and so on and so forth. The coordinate and also the size are fixed, are regular. For every pixel, we will always have the value. However, in the point cloud, we have the 3D coordinate, right? X, Y, Z, and this particular point cloud of here, the object here. The locations of the points, it just can be in any 3D coordinate, right? And the dot itself is, the size is also, in my opinion, is we cannot really define the size. Usually we define the size is just for the visualizations, but internally when we consume this data into the neural networks, we do not really have the size. Just point. So again, we cannot have regular data representations that in every 3D coordinate, we cannot guarantee that we always have the value. Most of them just empty. If we have like 1000, only 1000 exact coordinate, we have the point. So this is the first challenge. And then the second challenge is the permutations invariant. Let's go back to the image here, image example. Image is permutation variance. It means that if we permute the order, if we shuffle the order of this pixel, the output will be different. It variant to permutations. So if we apply a CNN, convolutional neural network, if we again shuffle the pixel position, the output of the CNN will also different, right? So CNN is by default is also permutations variance. And the challenge in the point cloud is it is again permutation invariant. It means that if we shuffle the order of this point, like if we have this table here, if we shuffle the order of the point cloud are exactly the same. If we have another order of the point in this table point cloud, the table itself is exactly the same. So if we have a 3D backbone, we should also have this property. If we shuffle the input order of the point, if we apply into a network here, the output features should be the same, no matter how we shuffle this input in the point cloud here. The output should be the same. So this PointNet is pioneer because it addressed this issue, and they proposed later, we will discuss. And let's see the use case of this PointNet. The use case that they demonstrate in their paper are, the first is classifications. So given any point cloud, we want the network to recognize what are the class of this point cloud. Is it a table? Is it a car? Is it a plan? And so on and so forth. And then the part segmentation is like given a point cloud of an object, we need to like segment the part of this object. Like this is the leg of the table, this is the top of the table. And if we have this kind of object, we can segment into, this is the body of the airplane, this is the wing of the airplane, this is the tail of the airplane, and so on and so forth here. This is the part segmentation. And then the semantic segmentations, given this, for example, indoor scene here, we want the network to segment the object based on the semantic meaning. Like we have a table here, we have another object is chair here, and this is probably window, and so on and so forth. Yeah, we need to like classify for every point here, segment them. Okay, and let's try to discuss the high level idea first, which is how we can achieve this permutation invariant property in this point cloud data representation. Okay, so given an input sample, for example, we have the point cloud of chair here with the number of points Rn here, and then this is the number of the coordinates, which is correspond to x, y, and z. Okay, and those n points will looks like this. We apply this into point cloud encoder, which is in this case is PointNet. We later will discuss the more detail how we can extract these features, and then we get this the number of point, which is correspond to the n here, the same, but we will have the embedding dimensions, right? The difference. So we map from the three coordinates x, y, z into another embedding dimensions. It can be, for example, like 256 and other embedding dimensions. And then PointNet, they introduce this block that make these point features are permutation invariant. It means that if we have this here n, this is the embedding dimension, no matter we shuffle this point, the output will be the same. How we can achieve this? And in the PointNet, they simply use max pooling. Yeah, this is pioneer work. In my opinion, this is still very simple. They use max pooling so that the output after we apply max pooling is permutation invariant. Let's see if we have this point features. This is endpoint. This is the embedding dimension. We do max pooling in the column wise here. So we do max pooling here. Takes the maximum of this column. Again, this is take the maximum of this column. Again, we take maximum of this column, and the output will be E. It's a vector 1 by E. I just remove the 1 here. Simply write the E here. So again, no matter we shuffle the order of these points in the input, the E will be the same, right? So that's why the whole pipeline here of the PointNet, they achieve this permutation invariance. Okay. So if we have this E, we can use this for classifications. We can just input this into the classification branch. For example, we can use MLP. We can map into the number of the class of the input in the dataset. We just map into their corresponding probability to do the classifications. And for doing the segmentations, we need to have this n by E. Later we will discuss how we can achieve this. But again, this is just the high level idea, which is the important of this point cloud understanding, which is the permutation invariant aggregations, which is in this paper they use max pooling. Okay, let's jump into more detail. This is the architecture of the PointNet. We have the classification network, which we can see in this blue color here. And then we have another additional branch for the segmentation network. We can see in this yellowish block here. Okay, let's go more detail for the classification network. Okay, so given the input point, in this case, we have the n points by 3. The 3 is again corresponding to the coordinate of the point, x, y, and z. We will exclude this input transform first. We will discuss later, just to make our understanding is easier. Okay, so this is still corresponding to this one. We exclude this for this particular discussion. And then from this point, endpoint here, we map this embedding, the 3 here, into another embedding dimension, which is, in this case, is 64. How we can do this? We can just use MLP. In this case, for every single point here, we apply an MLP. If we want to map from this 3 into the 64, we have this kind of MLP. This is 3, this is 64 features. So we just have the fully connected layers that connect this input 3 into this 64 features here. And after the fully connected layer, we have the activation functions and also those normalizations. Yeah, basically that's the building blocks of the MLP, multi-layer perceptrons. And then we use shared because we use the same weighting value of this MLP here applied to another point. So this is only for one particular point. We have n here, for example, 1000. The first point, we apply this MLP. The second point, we also apply using this MLP. And then until the last point, the 1000 point, we apply this the same MLP, and we get this output here, 64 embedding dimension. This is the output, 1000, for example, by the 64 embedding dimension. And then again, we skip these explanations for now, and I will discuss later. This is the output. We also apply another MLP. We will map from this size 64 into this size 128 here. And then we apply another MLP to map from this 128 to this 1024 here. And finally, we will have this output here. N is the number of points, and then 1024 is the embedding dimension. And again, we will have this max pooling, and we will max pool this dimension. We have n here, and we will have 1024 dimensions. We will max pool for every column here. This column take the maximum, this column take the maximum. Again, no matter we shuffle the order of this point, the output of this will be the same. So that's why this can achieve permutation invariant. And then we call this as global features because this features is only one factor that represent the global of the point. For example, we have 1000 point here. So in global point here, it is only represented by single factor, right? This is 1 by 1000 something here, and this is 1000 by 3. Again, this single factor represents all the points, so that's why we call this a global feature. And finally, for classifications, we will have this one factor. We map into another MLP into this embedding dimension by using the similar. So this number will be in this layer, and this number will be in the second layer here. Again, we also map into another dimensions, and in this particular paper they use this number as hyperparameters, but you can decide by your own. And then finally we will map into the k. K is the number of, oh, I think I should put something here. Oh, I think I haven't put, but anyway, the k here is the number of category, the number of class of the shape. For example, we have the human, we have the plant, we have the car, we have the table, we have the chair. Those all the category. We have the number of k, and we will just represent this every k here into associate with every category. Let's say we have 10 category, and then let's say during the training we will maximize based on the label. Let's say in this particular input we maximize in this 10 category of 10, and 10 is, let's say, associated to the chair category. So later if we input a point cloud of the chair, hopefully that our network can maximize the probability of this 10 column here that is associated to chair probability. Yeah, so this is how the classification network in the PointNet. Again, I think the basic building block is just MLP, which is very common. We also know in the other data other than point cloud. if we already like work on the image or other domain, data domain MLP are just everywhere. So the max pooling is also actually everywhere. This is just interesting is because this particular simple operations can achieve, can solve the permutation invariance property in the point cloud data. Okay, so that's it for the classification network. Let's see the TNet. We exclude to discuss about this block, and let's discuss why we have this. Okay, so TNet correspond to in this block, and also we have another TNet in this another block here. Okay, so in high level, the real world scenario, all the point cloud probably we will have a different pose, right? Different rotations. The chair can be aligned in the portrait or slightly rotated into a certain degree, in any degree. And also an object can be translated into the right or into the left or in any directions. We have this possible transformation, affine transformations, like translation, scale, shear, and also rotations. So the purpose of having this transformation is we want to make this network so that the network can tolerate this affine transformations in the input data to some degree. So if we have some input that have a possible rotations, possible translations, possible affine transformations, the performance should be the same, as good as if we don't have this kind of variance of this affine transformation. Yeah, so that's the motivations where we have the TNet. And we have the transformations in the input representation here, which is the 3x3 is just the coordinates of the point cloud. And also we have another transformation in the feature space here. We have the embedding dimension in this particular layer is 64 here. Let's discuss how we can get these transformations. So let's see that in this particular level, because the output is the tree here, we also want to map into the same, exactly same shape, n by 3. So to do this, we will learn a transformation metric, which is 3 by 3, because n by 3, if we multiply it by 3 by 3, the output will remain the same, right? N by 3. So yeah, this one. And then later we will multiply this one. Okay, so the purpose is we want to learn a transformation metric so that no matter we have a affine transformation here, the performance should be still as good as if we don't have any transformations. So this is the purpose of this transformation here. And then to estimate this one, we use this point cloud here, which is the n by 3. 3 is just xyz coordinate. And we will apply into the stack of MLP. And because of we want to estimate 3 by 3 transformation metric, we need 9 parameters. And we can just reshape into 3 by 3. And that's it. We have this one. And we just follow by metric multiplications, which is, this is the input and also the transformation metric, and result in this another data representation that is transformed from this input. And then in the features, also the same. The difference is just the dimensions. So here, because we have the 64 dimensions, we also learn 64 by 64. And we have another result with the exactly same dimensions, but it is transformed to tolerate this affine transformation. Okay, and another note is these transformations are initialized by using identity metrics. Yeah, I think this one is the motivations of the TNet. Okay, and then let's discuss another topics, which is how we can achieve segmentation task using this PointNet. So we already discussed before that we can extract the global features by using this pipeline. And finally, we will have global features that are permutation invariant. However, when we do the segmentations, we need to have local information instead of only global. global we already have here, right? So we also want to have this local information that can be captured by this network. And actually we already have this local here. Local means for every point we capture the locality instead of the global all point here. And in this case, in PointNet, because of this is a very pioneer, the locality is just the point itself. But I do not want to discuss too much in this video sections, because we will discuss further in the development of the next, which is PointNet++, that they propose more advanced to address this locality. Anyway, let's go back. So we have this local features that have the n by 64. We put here. This is local, and we have the global feature here, global here. And because of this is only one factor, we just repeat. This is one, and we copy into another row. We copy until the last, which is the n here. Okay, we concatenate these two features. This is capturing the local features, and this is capture the global features. So hopefully this global and local features can be used to carry the segmentation network. And then after we have this, we basically just apply another MLP. We map this particular embedding dimension 1088 here into another dimension, this one 128, by mapping into this embedding dimension, and then we map into another embedding dimension, and finally we will have this embedding dimension. So we will have the stack of 3 MLP in this particular block here. And then after we have this feature output, finally we will have another MLP to map this particular embedding dimension into the M. M is the, do I write something? Yeah, M is the number of the semantic class. For example, if we want to segment indoor scene, we will have those semantic, like the semantic of chair, table, wall, floor, and so on. This is just the number of M, and every M here is correspond to the probability of its semantic class in the indoor scene of point cloud, for example. Yeah, so finally from the output here we can just minimize using standard cross entropy to learn the probability distributions of the semantic class in the dataset. And after we train, we can use this learned weight here to predict any point cloud and segment them. Yeah, I think that's it for the segmentations network, and let's see the experimental result. And again, this is the pioneer, and I think as a pioneer of the 3D understanding on the point cloud data, I think these results are good. We can see that this back we have the segmented handle of the back and also the body of the back, and for the laptop we have the screen here, and also this is the corresponding keyboard part. And for the indoor scene semantic segmentation here, we have this the point cloud of this indoor scene. We can see that the corresponding point are well segmented. This is the wall, this is the floor, this is the chair, and so on and so forth. We can see in this slide here. Yeah, I think should be that's it. Before I end these sections, I will put some important notes. This is the motivations of why we have the next papers which address this following issue in the PointNet. So the first issue in the PointNet is the feature extractions. The captured local features are just simply point-wise, do not really consider neighbors. So let's see that in this particular encoder of the PointNet here, we map these 3 embedding dimension, or the original coordinate xyz, into this 64. And to construct this embedding dimension, this MLP only consider a single point itself. Here, this point here, only consider this single point, do not consider the neighbor's point. And then again, in the next point here, these particular features also only consider a single point, corresponding point, do not really consider the surrounding. So that's why this is quite weak local features, and this is not enough. So that's why later we have the PointNet++ that address this issue. And then the second issue is the alignment network. As we can see previously, we have the TNet to transform the input so that it can tolerate the affine transformation into some degree. However, those alignment is still very simple and is still relatively sensitive to affine transformations. So for example, if we have the network here and we have the data sets that are, let's say, all the chairs are aligned in this directions, portrait. If later we have a new data set with different pose, probably using the same network, the performance will encounter some drops because of this. This is not really tolerance. So later we have another papers that address this better. And then the third issue is related to the semantic segmentations. So if we have a very large 3D point cloud, for example, if we have 1 million points that construct this indoor scene data here, typically this PointNet and other pioneer of this 3D backbone, they split the large point cloud into 1 by 1 by 1 meter cubic here. And there are some issue if we doing this kind of splitting. The first is we lose the global relationship. For example, because we split this, we have this input into the network and segment them, and then in the next we will segment this particular splitted data here. We will lose the global relationship. For example, if we want to like recognize this particular chair here, if we merge them, the network can learn here, right? This surrounding, but because we split, we lose this global relationship. And then the second issue is after we apply this into this network and segment them, probably the segmentation result on these transitions are not smooth. Yeah, because they are predicted one by one, right? Not the whole scene. So that's why we probably will find this non-smooth segmentations at the transition. I think, yeah, it should be that for the some issue that we will discuss later. In particular, this 3 paper will address those 3 issues. I think that's it for this video sections, and see you in the next video.